In this demonstration, I wanted to discuss and show the multi-section solid and multi-section surface coupling mode, specifically the ratio coupling mode and what it means. So just a little quick introduction here. So I've got two sections. Disregard some of the annotation you see here. I'll get to that in a few minutes. But I'm in the part design workbench. And if I went to the multi-section solid tool and I select that section as the first section, and this section is, notice I've got uh, two sharp corners, what I would refer to as a G0 corner, or it's not tangent here. In other words, it's just a point. And then I've got a G1 tangency and a G1 tangency here on this section, and the same on this section. I've got a G0 tangency, G1 tangency, G0 and G1. So with the coupling modes in CATIA, there's four of them in the multi-section solid tool. You've got ratio, you've got tangency, and you've got tangency, then curvature, then you got vertice. So let's discuss these real quickly first, but I'm primarily going to be demoing ratio and how it works. But tangency, we'll look for, and I don't know why they call it tangency, but non-tangency corners. In other words, this is tangency is a G1 continuity. So it's looking for G0 continuity, which would be these two sharp edges, if you will, or sharp corners first. Well, actually, that's the only thing it would look for. So it will combine these two or couple these two together, and then the remaining ones will have a ratio effect. Tangency, then curvature would look for tangency or G0 corners first, and then look for G1 corners second, which would be here and here and here and here. I'm not talking about these two today. I'm going to primarily talk about ratio and what that means. So I'm going to select ratio, and with ratio, it does what is referred to as a curvilinear abscissa ratio. Now that's a mouthful, especially for me, but essentially what that means is if you're familiar with Cartesian coordinates and you have an x and a y axis, let's just stick with 2D here, an x and a y axis, you can take coordinates and map them or treat them similar to how you would treat an x coordinate as compared to a y coordinate and provide a ratio if need be. So as an example, with what I have on my screen, I've got my first section has a total circumference of 254.248 millimeters. And that's why you see that on the screen there. And my second section has a circumference of 342 millimeters. So different circumferences, but still four corners. So let me just preview this for you, and then I'm going to take it off the screen and without creating it. But you can see the connecting lines. These are called coupling lines, actually, and how the sections are joined together. That's the curvilinear abscissa ratio doing that for you. And it can produce a really, really bad surface if you're not careful, which, so as an example right here, you can see how this surface is definitely not what I'm wanting. So let's talk. So the primary purpose of this video is to talk about what does it mean to have a curvilinear abscissa ratio. And again, I apologize if I'm butchering that terminology. That's a mouthful for me. So, and I've got some annotations here for your benefit and my benefit as well. But let's look at the first curve. As you go around, as I said, it's 254.248 millimeters. So this, if I'm not mistaken, if I recall correctly, is 60 millimeters. And so the ratio, so if this is the starting point, which it is, and if I'm tracking this 60 millimeters up, that should be a ratio of 0.23 something. And I was a little more accurate here to 3 significant digits just for the purpose of this demonstration. I probably should have been a little more accurate on all of these instead of 2 significant digits, but that's a whole nother story. This first one is this first point. This first G0 point is 0.236 of the overall circumference. The second point located here is 0.43 something. That's actually, I could take this out to 3 or 4 decimal places, but it's roughly 0.43 of the way around. And then going around my curve here, getting to this third point, this G1 point, it's 0.48 roughly, going around the circumference, and then it's back to a ratio of 1. So think about these as ratios. This is 0.236 other way around. This is 0.43, 0.8, and 1. Same way over here. I've got 300 on this section. I've got 342.81 millimeters circumference all the way around. The first point is roughly 0.22 the way around. The second point, which is a G1 point, has G1 continuity, is 0.43 roughly around. This second G1, or the third total point, is 0.78, 8-ish, if you will, around, and then back to 1. So why is that important? Well, that's the ratio that's happening. So what I'm going to do here is I'm going to draw with the line tool how the coupling will look based off of these ratios. So what I'm going to do, so you can think, so I'm going to start the line tool. Let me double click so I can keep this active. So I'm going to start, and I'm going to work from the first section to the second section. And then I'm going to do the second section to the first section with my coupling lines. So I'm going to start, and I'm going to go from the points on the first section to the ratio points on the second section. So I'm going to go from this point. Oh, by the way, so this point, just to clarify here, so this vertex is 0.236 other way around. So what I did, this reference point, this is an on curve reference point. If I tap into that, and you can see this, that with the ratio is 0.236 around. So this point on this curve corresponds to this 0.236. This point corresponds to this 0.43. This point corresponds to the 0.8, and then the 1 and the 1s. So let's do this and connect there to this corresponding ratio point. Then I'll connect from, I'm grabbing the point there. That's not the reference point behind the scene, but I'm grabbing that vertex, that topological vertex, and then I'm going to the reference point. And then again, grabbing this topological reference point, vertex point, not reference point, vertex point, and then I'm going to this reference point. And then from here to here, 1 to 1. Now, let's go the other direction. So I've got 0.22. This point is 0.22 of the way around the circumference. So this point on the first section is 0.22 roughly going around. And let me show you what I mean by roughly. So that's 0.22. So, and then this point is 0.43. So I'll put a reference point. It's right there, which is also 0.43. And that just by the nature of how close they are to shapes, those are close to each other. Then I got 0.78 here, and then I'm going to a point that's 0.78 around the circumference, and then 1 to 1. So if I come in, I can select, and I can go, I'm going backwards, so I'm going from section 2 to section 1. So I'm going from a vertex to a reference point. Vertex to reference point. And vertex to a reference point. And there's no need of me completing this last one, even though there would be one there, but they would be right on top of each other. So that's what the coupling points should look like with the curvilinear abscissa ratio, in other words, or the ratio coupling mode. Well, let's verify that. So I'm going to go to the multi-sections solid tool, and let's go section 1 to section 2. Make sure my coupling mode is at ratio, and let's just hit OK. So let's see how these match up with each other. So notice how the curves I drew in match up close. I did probably do more rounding off than I should have, but notice how they're sitting on top of those lines I drew in, close at least, and with some round off error. So that is how CATIA will couple using the ratio coupling mode. Now keep in mind that might be okay in certain situations, but in my class at CMU, Central Michigan University, I do not allow my students to use that particular coupling mode. Just kind of I want my students to have a little higher quality and be more concerned with how the sections are coupled together. So I try to avoid that. But at least I like to talk about and show them, what does that mean when you're doing that particular type of ratio mode. So I could change this, and just for the sake of demonstration, now these won't line up with each other. But if I change the coupling mode to tangency, so I get some different coupling lines this time because the first two are coming together fine. So you notice I've got a nice couple between the first two vertices, first pair I should say, and I got a nice coupling between here because those were G0 points. But once I get to the any G1 or better, I should say, any G1 or better points, then it starts generating its new coupling lines. So you would have to do manual coupling or guides to take care of that. And let's see if tangency then curvature would work. It worked fine. So just by the nature of the model, it does notice it took away the coupling lines that were out of place. So that's by far, and notice the coupling lines are going from vertex to vertex, which is what I'm looking for. So but primarily I wanted to demo what the curvilinear abscissa. So I hope that helps. So primarily I hope that helps with an understanding of what the curvilinear abscissa ratio means in CATIA.